Hi, everyone. Today I'll be talking a little bit about how to do more scalable performance analysis for your MPI applications. So the first thing we're going to do is talk about some of the challenges we face in terms of doing scalable analysis, scalable MPI analysis, talk about some of the existing tools. And then we're going to delve a little bit into the MPI performance snapshot, which is trying to solve exactly those same challenges we had discussed before. We'll discuss some of the metrics that it reports, and then how to get the tool itself as it's part of the current beta. So some of the challenges, you can sort of qualify them in three different areas. When you're trying to scale out with your MPI application, there's a few issues, right? So first off is the scalability itself. Cluster sizes have started to grow potentially faster than Moore's law. What we really mean by that is we're adding more and more cores on a single machine, as well as adding more machines to a single cluster installation. So once you start taking advantage of, thousands to tens of thousands of MPI ranks, then you want to make sure you have a tool that can keep up with that expansion. You can't. It's pretty hard to do profile-based analysis at that point, just because the trace data that's gathered tends to then be in the gigabytes, few gigabytes, even more, maybe even a terabyte, which is really too much to handle at some point when you get to those thousands of cores. So what you really want is something that's more lightweight, something that's more scalable. It gives you just a high-level overview of some of the issues in your application. And then once you start recording that much data, what you really want to focus on is some of the key metrics. There's a lot of events, there's a lot of data you can record, but the hard part really is identifying which ones of those you want to really focus on in order to optimize your application in terms of scaling out to a large number of cores. So what is there out there today? So this is just an example of doing lightweight statistics through the Intel MPI library, which is our implementation of the latest MPI 3 standard. So if you've never used Intel MPI before, so the library itself keeps track of its internal statistics as the application is running. And there's also an option where you can print it out to the to a standard out, or a text file in this case. So here's just a quick example of enabling that functionality for the library. And it gives you good information, right? So I'm not going to say the information it provides is bad. So it gives you things like where are your potential communication hotspots. It gives you information about, what are the message passing patterns between the ranks that are doing, let's say, point-to-point communication, so doing send and receives from one rank to another rank. Same with the collectives, so which of your collectives are really your biggest consumer in terms of how many calls you're making and how much data you're transferring for each collective between the processes, as well as a breakdown of where sort of the biggest cost is in terms of communication. So for this particular example, you're spending a lot of time, about 7% of your total runtime was spent in that all-reduced call. So it might be a good idea to take a look at that. So while this information is great, there's a few things that are missing. Once you get, so this is fine if you're running, let's say 16, 32, even up to 100 ranks, you might be okay, right? But once you get to 10,000 ranks, sorting through all of that data is is near impossible. So you have to really know what you're parsing for in order to really extract the information that's important to you. It also just gives you information about only about your MPI communication. It doesn't really give you any information about your, let's say you have a hybrid application, about what kind of OpenMP threading you're doing internally. So what we've decided to do is we're going to take some of these lightweight statistics that are already provided by the library. So it's the MPI profiling without that extra overhead. We're going to combine that with some of the counter data that we can get both from the operating system and lower hardware levels. We're going to mix some secret sauce into it, and I'll talk, maybe I'll talk a little bit about that later. Mostly just means processing some of the data and then categorizing it in proper ways so that it helps you really focus on what are the things you need to work on first. And so based on all of that information combined, so we have something called the MPI performance snapshot. So you can see the screenshot on the right-hand side, just an example of some of the output, and I'll focus a little bit more about what that is later on. So what is the snapshot? So it's currently part of the Intel Trace Analyze and Collector. So if you've never used the Intel Trace Analyze and Collector before, it's a profiler for MPI applications, and it's distributed with our Parallel Studio Cluster Edition package. So what it does is it goes through your entire application, and it records events based on the MPI data or the MPI messaging that's happening in your application. So the Trace Analyze and Collector is a great tool, but unfortunately it has its limitations, which is one of the reasons why we've introduced this new MPI performance snapshot. So it's just a really easy way for us to separate that statistical analysis for the event analysis that the Trace Analyze is really good at. It's currently just available through a command line, and you can run that with your existing application. So I'll give you an example of how that's done. So what we've really done is we've enabled you as a developer to gather and even do analysis of the statistical information for your MPI or hybrid applications up to some number of tens of thousands of ranks. So we've done some testing up to about 32,000 ranks, and theoretically, the tool can scale much higher. So what it shows is it gathers up some of the underlying PAPI counters. So if you're not familiar with PAPI, it's just it stands for the Performance API, and it's available. So some operating systems already ship with it. Others, it's just a separate install. And it does, so all it really does is record some of those OS and hardware counters I mentioned before. So we extract some of that information. We also work with some of the internal statistics provided by both the Intel MPI library and our OpenMP runtimes in order to record some of those imbalances that might be happening in your application at larger scales. So what it really helps you is do that initial analysis at the higher core counts, figure out where your potential hotspots are, and then later on you can do the trace analyzer profiling at lower core counts to really focus on those optimizations. Just a few more advantages. I think I mentioned a lot of these, but so initially it just gives you a very quick, since it's just very quick access to your profile, to the application overall profile. If you do have any variations in terms of the performance when you're scaling out, those can really be detected a lot sooner. So the tool is fairly quick to enable, fairly easy to use. And then in addition to that, in the post-processing stage, we provide you with some recommendation as to what are the areas, the focus areas you need to do some more development for. In terms of benefits to the developers, it really just helps identify those large-scale performance issues faster. There's a few tools out there to do the analysis at larger scales, and I'll talk a little bit about why what additional information the MPI performance snapshot provides. And then so I'll give you an example of some of the of how you enable the tool. So it's actually pretty easy to use, even if you're not a very experienced developer, for either for MPI or for hybrid applications. So here's just a high-level comparison between the tool that you might be familiar with already, or in general just profilers for MPI applications. Scalability tends to be fairly limited. So I know with the trace analysis and collector, we've done some testing. It's about 4,000 ranks, and it ends up just gathering too much information for us to really make sense of. I mean, you can see an example here. For about 1,000 ranks, it was already over 17 gigabytes in terms of data. So looking at all of that is really going to be potentially confusing. It does gather event-based analysis, which means that it's not just lightweight statistics, right? So it's getting you get the full application profile, which is one of the things that the trace analyzer is really good at. But unfortunately, again, it could be overwhelming, especially if you're doing 1,000, 2,000, 4,000 ranks. On the snapshot side, on the right-hand column, you can see that we've done some testing up to 37,000 cores. So the tool was able to do really well at that scale. So it's really targeted to any applications that are between 1,000 and 100,000 ranks. The data that it gathers is much lower or much less than the event-based data gathered by the profiler. So for about 1,000 ranks, it only got up to about 1,000 gigabytes. And it's not, so unfortunately with the trace analysis and collector, the amount of data gathered could be close to linear in terms of the number of ranks when you're scaling out. But here it's not so it follows more of a curve, so it sort of hits a plateau at some point, and any additional information doesn't really depend on the number of ranks. It does take advantage of the underlying PAPI events in terms of the counter data, but it also uses the built-in statistics as part of the MPI library and the OpenMP runtimes. So it sort of gathers both of those and provides you a high-level overview of the application. So here's a bit more details about what is the information that's provided by the tool. So it combines the PAPI events. It combines the OpenMP ITT notify metrics, which is just a way for the OpenMP runtimes to sort of give us detailed data as it's running for whatever OpenMP regions you might have in your code. And in addition to that, it adds some wait time metrics for MPI, so it knows when you're starting an MPI call, when you're ending that call, if you're doing some sort of a long wait time in between due to some internal factors. Maybe you're blocking on a collective operation or something like that. And then it also adds some internal MPI statistics. So the metrics that it provides to you as a developer is the total time spent in MPI versus the total time spent in application. So just at a very high level, it gives you some data about the how much of your total time is really spent in potentially those MPI, blocking MPI calls. And it also gives you a breakdown of sort of the MPI imbalance as well. So generally, in I guess that's a pretty generic statement, but in a well-parallelized MPI or a well-parallelized application, you want to spend less time in MPI calls and more time doing actual computation. And so what you want to do is take a look at that ratio and figure out if the time spent in MPI is something you're expecting as a developer. And the tool also helps you sort of categorize if something is good or bad. But the time spent in MPI as is what you were expecting as a developer, or if it's higher than expected. It also gives you a breakdown of some of the message sizes and the transfer data. So I showed you a screenshot of the lightweight statistics that Intel MPI does. And it grabs all of that information and provides it to you. So it'll take, for all of your, let's say, point-to-point communication, it'll tell you on average how much data you're sending between ranks, as well as what some of your outliers might be, so where your min and max values are. And then if the delta between those two is significant, then it means that there's some ranks that are spending a lot more time doing MPI communication than others, which might be indicative of an issue. It also, so if you look just at the PAPI counters, we're looking, so some of the information that it provides is floating point instructions, as well as what percentage of your instructions are vectorized, which is pretty useful, especially if you combine it with a tool that helps you vectorize your application, something like the Vectorization Advisor. That's also part of the Parallel Studio suite, as well as just memory, just data on memory accesses, how many instructions are doing memory access, things like that. And then finally doing the MPI and OpenMP balance. So we already have internal hooks into our MPI library and our OpenMP runtimes. So we know exactly when, let's say, an MPI region starts or an OpenMP region starts. And then based on that data, then we know how that compares to the total, wall time of the application. So it's fairly easy to figure out if you have a potential imbalance in the code. So at this point in time, that we're aware of course, so we have to make that disclaimer. So that's sort of the only tool out there that will show you the OpenMP MPI imbalance, as well as the PAPI counters all in one place. And I know there's a few tools out there that provide you part of the information, but I always find it helpful if it's all sort of in the same location and you can get access to the data so much quicker. So it's just a good entry point if you're just getting started tuning your application for running on large HPC clusters. So it's sort of a good first step in doing that analysis. So as I mentioned first, it's command line at this point in time, and I'll show you exactly how you run it. So we found that doing command line is much easier rather than starting up a GUI, especially if you're going to do scale out runs at 10,000 ranks or something like that. So here's sort of what the tool. Here are the steps in terms of getting started with the tool. So as I mentioned before, the MPI Performance Snapshot is available as part of the Trace Analyzer and Collector, which is a part of our Parallel Studio suite. So if you download the latest version, and I'll have a slide on that. So if you download the latest version, then you just get it automatically. There's no separate download that you have to do just for this. It's fairly easy to set up your environment. We actually do this with all of our tools, even if you have the Intel compilers, if you have the Intel MPI library, if you have the Intel Trace and Collector, vTune, whatever it is that's part of our tool suite. We provide a handy script, either Bash or C Shell. So there's, in my case, I ran my example with Bash. That sets up your environment, which mostly just appends a few install and library paths to the path and LD library path environment variables. And that's really all you have to do in terms of setting up your environment. There's really nothing else. If you're running the latest version of Intel MPI, what you can do is just add the extra -MPS switch. That's really the only thing that's needed. So what that does behind the scenes is Intel MPI recognizes that runtime option. It finds the appropriate executables from your path, since you've already set that up previously, and then it pulls in the right executables it needs in order to start gathering the snapshot data. So if you're running, so in my example here, if you're running over 1,000 MPI ranks with your executable itself doesn't have to be compiled in any special way either. So if you've used the Trace, Analyze, and Collector, you know that it doesn't require you to do special debug runs or to do some sort of a non-optimized version of the executable. This could be production level executable, and then it'll still start gathering the statistics. And then once it's done, it'll actually print out some data that I'll show you in the next application. So it just gives you a high-level overview of some of the statistics. And then in order to do that extra analysis, to get the nice HTML output I showed you, you just run it through the MPS tool itself. So what happens after you do the MPI run -MPS, the tool itself creates two separate statistics files. So one of them is specific to the MPI statistics, and the other one is a little bit more generic. So it might include some OpenMP data, as well as a few other counter data from PAPI or a few other things. So all of that is, so you can provide both of those files as arguments to the MPS tool. That will do some post-processing of the data, and it'll give you that nice HTML output. And I'm planning on doing a quick demo so you guys can see what I'm talking about as well. So as I mentioned before, once you do the MPI run command with the -MPS flag, it actually prints some general data, some general statistics to standard out in order for you to see directly. In addition to creating the two text files, the two statistics text files, it also prints some data, sort of general data, to standard out, so you can right away see what the overall view is of the application. So here's just an example of the information that it provides. So overall, it tells you the total walk clock time, so how long your application took in terms of running over all MPI ranks. And then it also breaks it down, so it gives you the min and the max values of how long each of those ranks took to complete. So again, I mentioned this before, but what you're looking at here is, so you're looking at sort of the two outliers, right? So the minimum, so the rank that spent least amount of time versus the rank that spent the most amount of time. So what you want to see is that delta of, so in this case, about 3.5 seconds, 4 seconds, is that something that I should be worried about in terms of the total execution time, or am I okay with that difference? So in this case, it's probably fine, right? So Two ranks took about 30 seconds to 35 seconds, so it's probably not a huge issue. But if, let's say, your max value is twice the amount of your min value, that means that potentially you might have some imbalance. And then we also provide so based on the PAPI data that we get, we also provide some hardware counter statistics. So you can see here it gives you a percentage of how much or how many of your total instructions were floating point instructions, as well as how many of your total instructions in your application were vectorized double precision. So generally, especially if you know your application is well suited for vectorization, you can figure out if it's actually doing the right thing here or if it's not doing the right thing. You can also combine some of this with the data provided by, let's say, the compiler has really nice vectorization reports, or the new vectorization advisor tool that's also part of Parallel Studio. So you can sort of combine that data and figure out if you can add more vectorization to your application. But this just gives you, again, what it does is it gives you sort of a high-level overview. Is this a potential area that I really need to focus on if I do want to optimize or if I do want to scale to a larger number of cores? And then it gives you, how much of your total instructions were actually doing memory access. So that could also be a bottleneck in your application, right? So if you're doing a lot of going out to disk or versus caching, then that's something you want to take a look at as well. And then overall memory usage is sort of broken down at the bottom. So again, taking a look at the delta between the min and max is what's going to get you, what's going to help you figure out if it's, in terms of memory usage, if all of your ranks are well balanced or not. And then in addition to the PAPI counters, some of the other OS counters, we also get all of this data from the MPI library and the OpenMP runtimes. So what that really helps with is showing you if you have any potential imbalance in terms of both of those in your application. So for this particular example, you can see that we have over 200 of our seconds, of our total runtime seconds, were actually spent in potential MPI imbalance. So that adds up to about 73% of our total runtime. So it's probably something that we want to take a look at, right? So we want to do some further analysis on the MPI sections of our code to figure out if we can reduce some of that imbalance. Same with the statistics. So you have, since it's a hybrid application, it's doing a lot of MPI plus OpenMP. So about 80% of the total runtime is spent in these OpenMP regions. And we're also, I think for this application, it's only running about 16 ranks or so, but each rank is then doing, potentially, up to 4 or even more, spawning up to 4 or even more OpenMP threads. So you can see that the OpenMP regions are a lot higher than the MPI ranks. So once you're done, so this is sort of the final step. So the statistical information that I previously showed is given to you pretty much immediately. So right after you do the MPI run, all of that information is shown to you, and you get access to the raw statistical data. So in order to do the extra analysis, you have to do that extra MPS commands and provide the 2 statistics files. So once that's done, it provides a really nice HTML output that you can see here as an example. So we showed, so I previously showed some of the raw statistical data. So if you take a look on the left-hand side here, it gives you that same overall view of your application. It breaks down how much of your total time is spent in MPI, and then how much of that is actually an MPI imbalance. So it seems to be doing a lot of, MPI blocking calls. And this is based on me as a developer. I would know the application fairly well, so I know what kind of calls I'm making. So it seems to be making a lot of blocking calls. And then the rest of my time is spent in computation, but the computation can actually be divided up into time spent in OpenMP, which is good. So generally you want to spawn a bunch of threads in addition to your MPI ranks in order to do the extra parallelization, the extra task parallelization. But then you can also see a breakdown of then aside from MPI and OpenMP, then the rest of the time is serial time. And in an application that's parallelized, you want to minimize the amount of serial time, because that would be your ultimate bottleneck, right? So you're only as parallel as to the amount of serial time you have in your application. And all of that data is color-coded in the little circle, which is right in the middle of the screenshot here. So for the total clock time, you can see about half the time is spent in MPI and half the time is spent in computation. And within that computation cycle, the majority is actually doing OpenMP, which is good to see. And then it breaks it down even further. So on the middle, you can see how your breakdown, how your MPI time is broken down. And it gives you explanations in actual understandable English about why the value is marked as high, what that means for your applications. In this case, it means that it's communication bound. And then how the MPI imbalance is sort of tagged and what it means, right? So in this case, it just means unpredictable wait time for each rank, for each MPI call in your application. And then when I do the demo, I'll show you how it expands a little bit into the details. And then it does the same for the computation time as well, right? So it breaks it down into OpenMP time versus serial time, and then it categorizes each one. Is the time you spend in OpenMP okay? Is it too high, or is it negligible, which means that you don't spend almost any time in doing OpenMP calls? So in this case, it's about average, which tends to be fairly, good. But then it also breaks it down into how much of your total OpenMP time is actually imbalanced, and that imbalance is then marked as high. So what I want to do is I want to take a look at how I'm distributing my OpenMP threads. Potentially, I want to take a look at that with, let's say, vTune, and figure out where the potential bottlenecks are. And then finally categorizes, how much of my total time is serial time, and then it defines whether that's a good value or a bad value. Generally anything that's fairly low percentage in terms of serial time is going to be good. So let me try and do this demo really quickly, because I can tell you that it's pretty easy for the use. For the tool, it's fairly easy to use, but you probably won't believe me until I actually show you. So I'm logged into a local machine here, and I have, so if I do let's say an LS, you can see that I have this Poisson example. So the Poisson is just a two-dimensional grid. It's doing nearest neighbor data exchanges, and it has some boundary conditions when the ranks have to communicate with each other. So I have precompiled this, and I've precompiled it with the latest versions of the Intel tools. So now I want to run MPS. So what I'm going to do is I'm going to source the latest version of the Intel MPI library because I want to be using the latest runtimes available. So to do that, I mentioned before, you can easily just set up your, you can just source your MPI vars and the same with the Intel Trace Analyzer and Collector. So I've actually installed the latest versions of both these tools. MPS first. So right now my environment is set up. The only thing I really have to do is simply run the application. So to do that, I do MPI run and I add the -MPS switch. And I'm going to say just 32 cores. I mean, this machine is not very large. And then I'm going to run my Python example. And it's going to think for a little bit. Once it's done computing, so it gives me the output of the application itself. But it also gives me some of that data I had shown you previously. Now, if you can see, let's just quick clear. So if I do another ls, you can see that it created the statistics file for the application I mentioned, and it also created the overall counter and some of the, if there were any OpenMP, then some of the OpenMP statistics as well. So it created both of those files. So what I'm going to do now is run the MPS tool, and I'm going to provide the two statistics files as arguments, and I'm going to let the tool handle that. So you can see it showed, so it did a printout of that example that I showed you, but in addition to that, it also created this HTML file, MPS report.html. So that's the one that I want to go ahead and take a look at. So I had transferred that earlier to my machine, so I don't have to bore you with waiting for it to download. So this is more or less what it looks like. This is a high-level view. As you can see, it sort of gives you that same the same breakdown of MPI versus computation time. So I'm actually going to zoom in a little bit. Hopefully you can see better in terms of some of the statistical data. So what's really cool about looking at this through the HTML view is that if you hover over each particular section, it actually gives you tips about what area you're looking at currently. So in this case, I'm looking at my total MPI time, and then it also gives me an explanation of what it is, and then whether that value is high or low or average. So in this case, it's high, right? So it's just sort of the same data that's shown on the right here. And then if I hover over this side, I think my resolution is not too high, but it also gives me then more details on the actual computation time. Now, if we look at the right-hand side, it gives me that same breakdown. So this application was actually much shorter than the one I showed in the slides. So it only took about 2 seconds versus over 200 seconds. So the MPI time here is still high, and the application is still communication bound. But what's interesting, if you hit more details, it actually gives you some further ideas about why this might be happening, right? So high, in this case, maybe high wait times inside the library. And it also gives you tips on getting further information or getting more information out of the tool by enabling specific runtime switches in order to get access, more detailed access to some of the data specific to, let's say, the MPI imbalance. And it's the same here as well. So if you take a look at more details for the imbalance, then it actually gives you a suggestion of using the trace analyzer and collector. So if your imbalance time is high, using the trace analyzer and collector in order to do some further analysis. And then it's the same. So this particular application actually didn't have any OpenMP time. Sorry, it didn't have any OpenMP region, so it's pure MPI. But it gives you a breakdown of what your serial time is. So over half of your total compute time is serial. So what you want to do is maybe do some more parallelization, or potentially look at vectorizing some of that as well. Okay. So now that so that's sort of the idea behind the lightweight analysis. So the tool can give you so it records quite a bit of statistical data, and if you look at the sort of the more details drop down, you can figure out ways to extract it even further. But what's important here is this is just the first step in your analysis. What you want to do now is take some of that lightweight analysis and figure out what areas you need to focus on in order to do further analysis. So if, let's say, your application is communication bound, then taking a look at some of your MPI communication patterns and doing analysis on those. Or if your application has a high OpenMP imbalance, they want to take a look at some of those regions and then figure out how you can optimize those. So that's sort of done through, so there's a couple of other tools you can use, first of which is the trace management collector. So if you've never used that before, it gives you a more detailed event-based data of your entire application runtime. So if you look at the screenshot at the bottom here, this is the same Poisson example. But all that really shows you is just a breakdown of how much of my total time is spent in sort of non-MPI routines and how much of my total time is spent in MPI routines. And then if within my MPI regions, then how is that communication pattern then affecting my total MPI imbalance, right? So I already figured out, so by using MPS, the performance snapshot, already figured out that I have a high MPI imbalance. And so here, it's obvious why, right? So it seems like in my MPI regions, I'm actually forcing some sort of a stair-step pattern or serial execution that forces each rank to wait on its neighbor to finish before it's able to continue, which is not, so obviously this is not very well balanced application. And then it gives you, it also does comparison. So after I fix the problem just by using non-blocking communication, then it gives you just a quick overview comparison between the sort of the initial run and then the after optimization run, or after I changed the code run, to see how those really compare. It can also do, so the tool itself is, it does full MPI profiling, so you can do, you can aggregate some of the data that you have shown, both for the MPI routines as well as the processes, so you can do aggregation and see how your communication patterns are between different machines rather than individual ranks. You can also do tagging and filtering of the data. I showed you can do comparisons, and then it also has a whole bunch of other features. So if you're interested in finding out more, you can just go to our website. We have a bunch of videos that talks about how to use the tool itself. But so this is the next step. If, let's say, the performance snapshot has shown you that you have a high MPI imbalance, then this is the next step you can take. You can go and do some profiling of less number of cores. So as you can see here, it gathers a lot more data. So you want to sort of reduce the sample size of the application and then figure out where those imbalances might be. But if, on the other hand, the snapshot tells you that you actually, you're okay on the MPI side, but what you really want to focus on is do some optimization on the OpenMP side, or maybe even you have too much serial execution in your application, then what you can do is you can run the VTune Amplifier XC. So that tool, so I feel that tool is, people should generally be very familiar with it. But one thing we have added recently is if you have a hybrid application, and that's supported, so that's supported by the trace, analyze, and collector, and it's supported by the MPI performance snapshot as well. So if you have a hybrid application and you're profiling it with the trace, analyze, and collector, and you figure out that you have a couple of ranks that are sort of lagging behind, or however many, maybe 2 or 3 ranks that are sort of lagging behind the rest, and you want to focus a little bit deeper into why that's happening, you can't. So the trace, analyze, and collector does really well with MPI, so it gives you really detailed data on that MPI communication. But once you get to the OpenMP regions, what you really want to do is take a look at it through VTune. So what the trace collector can do is you can actually automatically create that command line for you, so you can rerun your application with MPI under VTune, and then get that profiling data for VTune as well. So that's done just through right-clicking and then selecting the appropriate processes you want to do profiling on. And then once you have that command line, you can go ahead and do the analysis with VTune. Again, VTune, I don't want to spend too much time on it, but it's a great tool. It's a great profiler. It's really meant to help you figure out if you have a threaded application, what the issues are, what the hotspots are within that threaded application, or if you have a large chunk of the execution is really serial, then it can also help you figure out where the potential hotspots are, where you might want to focus on some of your parallelization or optimization efforts on. So all of these tools are available as part of our beta. So the beta is open today. It's open to the public and it's free, so you're welcome to register. You can look at the bit.ly link on top in order to go there and register for it. It really so the Parallel Suite contains all of our HPC tools. So it contains our C, C++, and Fortran compilers. It contains all of our performance libraries, such as the math kernel library, Intel MPI, the OpenMP runtimes, and then a few other ones. It contains all of the analysis tools. So that includes VTune that I just talked about. It includes the trace, analyze, and collector, as well as the MPI performance snapshot that's shipped with the trace analyzer. It also includes Advisor that has this new Advisor XC, which has this new vectorization advisor feature to really help you identify some of those vectorization opportunities within your code. So all of that is available in a single package, and we also have a couple of new things. So one of the new libraries we're introducing is the Data Analytics Acceleration Library. So it really helps you if you have any big data problems, if you want to do analytics on big data. It really gives you those optimized routines for Intel architecture in order to solve some of those big data challenges. So the beta opened in April, and it's going to be open until about, I want to say, start of July or so. So you're welcome to take advantage of that. And there's some functionality that's available in the beta that might not be available in earlier versions of the tools. So that's pretty much the end of my presentation. So I wanted to give you a few resources. So there's a sort of getting started guide. You can get the link here. That goes through the example I showed you. So it goes through running that closed-zone application. It gives you the steps on how to do that, and it gives you some of the output. If you want to learn more about how to use the trace analyze and collector, then you're welcome to go to that website and look at some of those videos. There's also a reference to the full Parallel Studio XC suite. So if you want to download an evaluation for the suite and grab all of those tools, you can do that through this website. The post-home sample code I showed you is actually available. So if you grab a version of the Parallel Studio, it's actually shipped with the trace analyzer and collector. So you should just go, if you install everything, go into the examples directory. It's actually right there for you. And if you have any questions or you're using the tool and there's something you like or something you don't like about it, then you're welcome to post to the forums, which are public, or you can get in touch with us directly. You can either just send us an email or, and my email address was at the beginning of this presentation, or you can also do, you can post through the Intel Premier support site. And I wanted to leave you with one last call to action. So as I mentioned before, the beta is open, so please register for it. So one thing I can say is for the MPI Performance Snapshot, which is what we talked about today, the HTML output is actually only available, was only recently added to the beta. So previously you would just really have to take a look at the you have to look at the sort of the raw statistical data in order to do some analysis. But now you can get more details through the HTML output as well. The tool is new, so it's recently been added. So if you look at the bottom there, it was recently added with the Trace Analyze and Collector version 9.0. We would love to get your feedback on it. Mostly if there's something that you're interested in adding to the tool that you feel it might be missing, then we're more than open to working with customers and working on their requests. What we really want to see is help the tool grow in order to really be beneficial for you, since you'll be the ones using it sort of in the longer run. In terms of requirements, probably the easiest is just to download the latest beta versions and use those when you're doing the analysis. But really, it should work with the latest released versions of the tools as well. So if you have Trace Analyze and Collector 9.0 Update 3 or MPI Library 5.0 Update 3, then those should work just as well. So thanks for your time today. And Mike, are there any questions?
Yeah, we've had several questions, and we've had some of our experts in the background answering quite a few of them. And we still have a few more minutes for anyone to go ahead and send in your questions. We won't be able to get to all of them at this time, but we will make sure you get an answer either through our webinar over the next few minutes or through an email later on. And also, before we get to a question, there is a survey. As you leave this webinar today, we'd ask if you could just take a few minutes to fill that in and give us some of your feedback. One question asks, do you have any plan to support I/O profiling in MPS?
Yes, so it has been requested before. We have talked about it. There's no, I guess I can say there's no plans to do it in the next version, so it's not there in the beta, but it is something that we can definitely consider adding down the line. So what we generally like to do is if you have a particular request like that, get in touch with us so that way, so we submit internal feature requests to our developers. It's really great to have a customer name associated with something like this so that it raises the priority. So you can either post on the forums and let us know that's something you're interested in, or you can email me directly and I'll get that request through the pipeline.
Okay, let's see, there's quite a few. What about, can you address how does this work, or does it work on the Xeon and Xeon Phi?
Mm-hmm. Yep, so this fully supports Xeon Phi profiling as well. So as with anything, as with any MPI application, you're planning on running on a mixed mode, so that means Xeon host and Xeon Cycle processor. If you're planning on running the MPI ranks on both of those, then you just need to make sure that the appropriate libraries and binaries are available on all machines. But otherwise, the performance snapshot does, in the latest version, does support Xeon Phi. So also do you'll also do Phi MPI profiling as well.
And can we select which PAPI counter to collect?
That is a good question. So I think yes. I think there's a way that you can do sort of selective filtering of the counters. But let me check on that with the developers, and I'll get back to you. So for a lot of the counter data, we actually rely on the PAPI interface. So you'll probably there's probably a way to do filtering through some sort of a PAPI config file.
Okay. Well, let's see. There is another one here. I think maybe we have time for one more quick one. What are Intel's plans for profiling energy use of a code?
Energy use, well, that's an interesting question. So we do currently have a separate suite that focuses on power consumption, and it is not something that's part of our it's not something that's part of our Parallel Studio suite. But what I can do is I can follow up with you offline and give you more details on some of the other tools or some of the other functionality that's available if you want to do some power profiling of your application.